free living bacteria. So you will see the samples or the video in a few minutes. The bacteria inside the wastewater, you can see them are very small like this under the microscope. So this type of microorganism will eat any free living bacteria. And of course, there is something called activated sludge flock. It's a big flock, or sometimes it will be broken down into small flocks. You can see that this protozoa will eat some part of the flocks, not only eating free living bacteria, also the bacteria attached on the activated sludge flock. Of course, protozoa is one type of microorganism that produce, if they found in wastewater, they produce a clear effluent, clean up all the organic or all the bacteria found in wastewater. Okay, so now, as we said that wastewater protozoa, it indicates that the system is healthy. So the wastewater system is healthy, and also indicate that the sludge age is in good condition, because these are the two things that we look at if you want to look at the stability of your reactor. The stability is based on the system health and of course the age of the sludge. Okay, so this is protozoa. Now we come to the naked amoeba. This also, you can see it here. It's an example of a naked amoeba, sorry. So this is a naked amoeba, look like. Okay, and this naked amoeba feed also on bacteria. You can see that these small bacteria found, you can see that most of the wastewater here is cleaned of free living bacteria. But this amoeba is famous in eating bacteria. And of course, it will feed on clear fluid around the flock. See, these are the flock. Okay, so the fluid around the flock, all over. This is a huge, big flock. Okay, this solid particle is a flock. And this is amoeba is dominant during shock loads. So if you have a shock load, you will see a lot of amoeba. Okay, shock load of what? If you have spikes of BOD, which is the organic content, if really high, and what level, you can see a lot of amoeba. And of course, if you have high particulate levels, so high BOD levels and high particulate levels. Of course, under adverse conditions, amoeba can have and can secrete gelatinous shell. Now it has naked amoeba, but later on, if there is an adverse conditions like toxic, high concentration of BOD, or high particulate levels, you can see that this will have a gelatinous shell around it. Okay, there is something also that's found in wastewater called testy amoeba. The testy amoeba also, you can see it like this solid is the testy. It looked like different. The other one was clear. This one you can see it's like solid. Okay, it's solid amoeba, and you can see this is a flock. It's feeding on the clear fluid around the flock, and also in bacteria. So this testy amoeba is eating bacteria on the flock and feeding on the bacteria himself around the fluid all over. So you could see that this might have some fluid, might have some bacteria around that this amoeba should be looking for too. This testy amoeba is dominant during shock loads of BOD, same thing of the other one, and high particulate level. And this amoeba, if you have low DO, low dissolved oxygen, and toxic condition, this could be able to survive, even though there is some toxic chemical condition for other type of microorganism. Flagellates. Well, this is not as clear that what you're going to see in the video, but this flagellates, you can see them, it's very small, and they have a flagell, a tail that will push them around. You can see there is another flagell. You don't see the flagell out of it, but later on you will see it. It's not clear in here, but you'll see it later on. They're going around. And these flagellates prefer what? soluble nutrients. So any food that is not particulate soluble inside the wastewater, oh, the flagellates will love to eat it. So anything that's solubilized inside the wastewater, the flagellates will love to eat it. Because also these flagellates cannot compete with bacterial growth rate, because bacterial growth is huge, easy to grow every second. Flagellates are not easy to grow like bacteria. And if flagellates are found in wastewater, it's indicative of what? High soluble nutrient levels. Okay, so if you see this in wastewater samples, this indicates that we have high soluble nutrient levels. Nutrients mean food. You'll have high soluble food levels. When you say high soluble food levels, you will see this later on with this conversion F over M. This is equivalent to food over microorganisms. So if you have high F over M, you would see flagellates all over the sample. Sometimes you will see swimming ciliates. So this is an example of a swimming ciliates. Look at this. You can see this is the head and this is the body of the swimming ciliates. You know, if you see swimming ciliates, you could see that this biomass is healthy. So the bacterial biomass is very healthy and the growth is very healthy. When you see this, you could indicate that this is a very healthy biomass. Okay, and the growth is very, very good. And of course, if you see a lot of these swimming ciliates, high of those indicate a cloudy effluent due to elevated levels of free bacteria. Okay, so if there is like turbidity because of all these swimming ciliates, you could indicate that there is a high level of free bacteria. This is swimming ciliates. Okay, since we are dealing with microbial and microorganisms diversity, let me just show you this figure. Let's say that the age of the bacteria or the age of the sludge. Okay, if the bacteria or if the microorganisms is young, this way. If the microorganism is old, is that way. Okay, and this is the bacterial population increasing that way in the y-axis. Very young bacteria, very young microorganisms, you would see amoeba and flagellates. This is slow growth, very young. When there is rapid growth, you would see swimming ciliates. Okay, now when the fast growth but slowing, it's not like as young and rapid growth. Fast growth, but not as rapid as this, and slowing. This is the healthiest side of any system. So our system, we need to have stalked ciliates. We'll be talking about these figures in a few figures of these microorganisms in a few seconds. We need to see floc structure. Activated sludge floc structure is very strong, and we need to see low filamentous bacteria, and this we'll see in a few seconds too. This is healthy. Now, when the growth is stopped, this is still healthy, but death is not occurring. So you can see bacteria storing nutrients in EBS, producing food floc structures, and some stalked ciliates colonies and rotifires, you'll see them start to appear. Still, the system is healthy from here to here. Now, if you want to design a reactor, which side of this sludge age versus bacterial population we need to have is this side. We need to have the healthy system. If you see this and this and this and any one of those, now your system is fine. If we are seeing this, not good. You need to make the microorganisms old enough so they could degrade more organics, and if you could keep the healthy microorganisms in the system. Now, when the microorganism become older, in the old stage, you will see Nocorodium forms, rotifires, nematoids, flock is being destroyed, flock disintegration, and bacteria starvation. Well, we don't need the bacteria or the microorganisms to come to this level, because this means everything is going down. So we need this type of healthy microorganisms. Okay? So if you take a drop of any wastewater from any reactor, from a CMFR, from an SPR, from a plug flow reactor, if you see this by itself or this by itself, this is young microorganisms, and that's not what we want. If you see any of those by themselves, this is old microorganisms. We don't need this. We need it always in the healthy side of this figure. This is also a crawling ciliates. You can see that it has crawling ciliates. Okay. You can see that there is hair, and it will crawl around the activated sludge flux. It will crawl around. This is an example of an activated sludge flock. It's a flock. Okay, so you can see the bacteria will hide inside. The bacteria will be at the surface. Organics also will be around, attached to the activated. This is it. Look at this. This is the huge activated sludge flock. This is the flock. This is the flock. And this is the crawling ciliate. It crawl on wastewater. Also will crawl in the activated sludge flux. This is common in healthy activated sludge. It helps clean up the flock structure. So anything here, it will clean up the flock structure from any organic. Okay? This is dominant when dispersed bacteria begin to form flock. Ammonia levels are low and pH levels are around neutral. So these are the conditions that the crawling ciliates will occur. And the crawling ciliates indicate longer and more suitable sludge age in comparison to free swimming ciliates. Okay? Stalk ciliates, you can see it looks like a flower. You can see it's a stalk. From here you can see that this is a stalk. Okay, and this is the mouth, and these are the hair cells in the top to push the water with organics inside, so they could degrade all the organics and eat all the organics found in the wastewater. And of course, digestion will start happening inside the ciliate itself. And this stalk ciliate is attached to the activated sludge flock. You can see it. This is the activated sludge flock. So every activated sludge flock has all these stalk ciliates. Look at this. A lot. Okay? Sometimes you'll have double stalk ciliates. This is common in healthy activated sludge. We need this in healthy activated sludge with significant BOD reduction. So BOD will start coming into the system around, let's say, 300 milligram per liter. This is in, and leaving, let's say, out at around 19 or 20 milligram per liter. This is very good reduction of biochemical oxygen demand. So this is good with a significant BOD reduction and healthy activated sludge, and this can help clean up bulk liquid. A lot of liquid with organic can be treated with stalk ciliates. So this is dominant only when high levels of flock-forming bacteria are present. You can see these flock-forming bacteria are present. These are dominant because they could attach to them. And of course, colony formation indicates aging sludge age. Okay? There's another stalk like a ciliates like this attached tube. It's attached, but here it's attached to a flock, this flock of bacteria, and it looked like a tube ciliates. You can see it. It's a tube, and there is hair all over. The main reason for the hair is to allow the water to come in, to come in inside the tube ciliates, so they could eat all the organics found in wastewater. This feed on bacteria, algae, and smaller protozoa. So it will eat the protozoa that we were talking about in the previous slides. This indicates what? Long sludge age, a little bit aging here. And of course, sufficient BOD removal is good once you have this tube ciliates in. Tube ciliates will form surrounding membrane in response to unfavorable environmental condition. So you could have membrane around it in case if there is any toxic chemical coming in to the system. Okay? Now, mitosa is one example that you might see in wastewater, and these organisms indicate overall health of wastewater treatment system. And this mitosa is often associated with older sludge age. Okay? And this is common in a lagoon. You know the meaning of a lagoon? It's not like SPR, it's not CMFR, it's not CSTR or a black flow reactor. Lagoon is like a hole close to a factory, and they dispose all their wastewater, whether this is oily wastewater, whether this is like dairy wastewater. And of course, there is a little bit of mixing, and they allow air to come in from outside, so we could allow aerobic degradation. And of course, effluent will come out cleaner, and we call this a lagoon. Of course, lagoon will not treat wastewater as good as CMFR or black flow reactor. Rotifiers. So let's look at the rotifiers. They look like this. Rotifier. Look at the legs. Look at the legs. These are the legs, and these legs should be attached to a flock. And you can see the shape of this rotifier. Okay, look at this. It's a nice looking rotifier. This rotifier consumes dead and decomposing organic matter. And this rotifier is dominant only after most food, most nutrients have already been removed from the system. So if you have, as we mentioned before, F over M, if it is low, then you could see rotifiers. Okay? So dead rotifiers are a strong indicator that there is some toxic chemicals entering to the system. So if you see dead rotifiers and not functioning very well, which means that there is some toxicity in the system. Nematode, and this is bad. Nematode is bad. You can see it, it looked like a snake. It looked like a snake. It looked like a snake. You can see it? It looked like a snake. Okay? It consumes bacteria, fungi, and other nematodes. So they eat other nematodes. Okay? This is indicator of an old sludge age. Okay? This indicates that the age of the sludge is very old, and we have to control it. We have to make it a little bit younger than this, all the bacteria. All the age of sludge. Okay. Tardigrades or water bears. Look at this, water bears. Up. Let's just raise this. Okay, let's look at this. Water bears. Okay, it's like a bear, and you will see it once we come to the feed. You can see how the bear is moving around. This bear could consume protozoa, metazoan, and bacteria, and able to survive of oxygen deficit. Low, very low dissolved oxygen, but are sensitive to toxic condition. So even if you have toxic condition, this could survive too. Okay? Bristol worms, another example of worm that we don't want this to happen here. This is a Bristol worm, a huge worm that's, we don't want this to be shown in samples, but if you find them, it means very old sludge age. And growth is of these worms are stimulated by high MLSS. We will be talking about MLSS once we come to biological treatment. Mixed liquor, suspended solid, and of course high of this, high MLSS, and of course low F over M, low food over microorganisms, and high nitrate levels. So this will show if there is high nitrate levels. So high nitrate. So if someone saw a Bristol worm like this, you could see that it's either increased high mixed liquid suspended solids, reduction of food over microorganism ratio, and high nitrate levels. So you can see the Bristol worms. Why we are studying all of this? Wastewater is a biological process. For us, we have to analyze the microbiology of the wastewater. We need to understand the overall health of the system. So the overall health of the system is very important if we need to use the bacteria, and if you want to make this bacteria and microorganisms healthy in order to clean up your wastewater, you need to understand the microbiology of the wastewater. And of course, we have to propose solutions to the problems based on